Humanoid robots malfunction and crash at Beijing World Robot Conference. The futuristic promise of humanoid robots met a very real engineering challenge at Beijing's World Robot Conference, where several advanced machines reportedly lost their balance, crashed, and required repairs in full view of visitors, engineers, and potential international buyers. Now it's time to break down every angle of this story on our AI podcast.
A multi-million-dollar state-of-the-art bipedal robot. Like, it is an absolute masterpiece of modern engineering, and it's standing right in the middle of a brightly lit exhibition hall and is currently face-planting, just in a shower of bright sparks right in front of thousands of international buyers and engineers.
Yeah, it wasn't a soft landing either.
No.
The machine was trying to stabilize on its left leg, and it started wobbling, couldn't recalculate its balance in time, and the entire metal chassis just tipped forward right into the protective padding.
Oh, man.
It actually damaged its waist joint on impact.
Which is just an incredible visual to start with. So we've pulled together a massive stack of sources for this deep dive.
Yeah, we have.
We've got engineering journals, on-the-ground reports from the World Robot Conference in Beijing, and a bunch of industry white papers. And the mission today is to cut right through the glossy sci-fi movie hype surrounding humanoid robots and look at the gritty, sparking reality of where the technology actually stands today. Because that crash happened right in the middle of this staggering event. This was between August 19th and the 23rd, right inside the Beijing Yizhuang Exhibition Center.
Right.
Stretching over 50,000 square meters. They had more than 300 companies there, over 2,000 robotic units on display. But out of all the polished demonstrations, that one dramatic failure completely stole the show.
Well, what's fascinating here is that while the general crowd might gasp and see, a massive, expensive malfunction.
Right, like a disaster.
Yeah, but the robotics community sees something entirely different. That crash is actually a vital, revealing look at the extreme difficulty of operating in real-world environments.
Oh, really?
Yeah, it pulls back the curtain on just how punishing this specific engineering problem really is.
Okay, let's unpack the mechanics of that because it feels a bit counterintuitive to me.
Okay.
I mean, we live in a world where AI software can write complex code, it can pass medical exams, generate video from text. So if the digital brain is so advanced, why does a cutting-edge physical machine just fall over while standing still? I would assume the static balancing is the easy part.
You'd think so, but standing and walking on two legs is staggeringly complex from a biomechanical standpoint.
Is it?
Oh, absolutely. We don't appreciate it because human beings do it subconsciously. Like as you walk down a street, your brain and your nervous system are making millions of micro adjustments in muscle tension, posture, weight distribution.
Right, without even thinking.
Exactly. You feel the slight dip in the pavement, the shift in your center of gravity,
Right.
and your body compensates instantly.
So to translate that to a machine, they have to recreate that entire biological nervous system using cold, rigid hardware.
Right. And that involves a massive amount of real-time processing. The robot is relying on this array of cameras, gyroscopes, and force sensors embedded in its feet.
Wow.
And the onboard computers have to constantly calculate a three-dimensional center of gravity. I mean, it has to know precisely how much downward pressure is being applied through each mechanical toe.
Each toe.
Each toe, yeah. It has to measure the friction of the floor surface and then send electrical commands to adjust its joints.
So it is like trying to balance a heavy wooden broom vertically on the palm of your hand, but you're doing it in the middle of a windstorm.
That is a brilliant way to visualize it, yes.
Like every single gust of wind, or in the robot's case, every slight shift in momentum requires an instantaneous, perfect physical reaction.
Exactly.
If your hand moves a fraction of a second too late, the broom is gone, it's falling.
The margin of error is virtually zero. If there is an unexpected tiny shift in the robot's own weight, the control software has to recognize that problem and send a physical correction in milliseconds.
Milliseconds.
Yeah. If the latency between the sensor detecting the wobble and the motor reacting is too high, the robot crosses a geometric point of no return.
Oh, wow.
Once gravity takes over beyond that specific angle, the physics simply dictate that recovery is impossible.
Which explains the sparks and the broken waist joint on the exhibition floor.
Yeah, exactly.
But looking at the engineering journals we have here, this raises an obvious question. If walking on two legs is this much of a logistical nightmare and requires this insane amount of computational power just to stand still, why are we brute forcing this?
What do you mean?
Well, why don't we just design these robots with treads or wheels? A wide base with 4 wheels is completely stable. It doesn't need to calculate its center of gravity thousands of times a second.
Right. Yeah. It is the most common critique of humanoid robotics.
Okay.
But the insistence on two legs actually has nothing to do with the robots themselves.
Wait, really?
Yeah, it has entirely to do with the environment they need to operate in.
Oh, I see.
Our entire physical world, every staircase, every doorway, the width of a factory catwalk, the pedals in a vehicle, the height of our kitchen counters, all of it has been meticulously designed over thousands of years around the geometry of the human body.
Right. We've built a world exclusively for bipeds.
Exactly.
So if you drop a wheeled robot into a normal building, it gets defeated by a single step.
Or a ladder, or a thick cable lying across a warehouse floor. The ultimate goal driving this industry is to create what they call general-purpose platforms.
Okay, general-purpose platforms.
Right. The economic dream is to manufacture a robot that you can drop into existing human infrastructure without having to spend tens of millions of dollars retrofitting the building.
Oh, that makes total sense. And the sources from the conference really highlight this shift toward industrial integration. There's a company mentioned in the reports called Liju,
Yes.
and they had their humanoid robots demonstrating exactly this. They weren't just standing there on a stage, they were handling large storage boxes inside simulated factory environments.
Right.
They're demonstrating how a humanoid can just walk into an existing logistics workflow, grab a box off a standard human height shelf, and carry it away.
And notice how the complexity scales up there. Once an engineering team solves the static balance problem, they have to introduce dynamic payloads.
Right, because the weight is changing.
Yes. When a robot picks up a heavy storage box, its center of gravity instantly shifts forward.
Right.
It has to continuously recalculate its balance while walking, carrying a mass that might shift inside the box.
Wow.
And factories are the immediate target market for this. However, there's a massive chasm between a controlled 5-minute stage exhibition and the reality of a real industrial workplace.
Well, sure, because I imagine a stage demo is heavily rehearsed. Like, the floor is perfectly flat, the box weighs exactly what the software expects it to weigh.
Yes, and that brings us to the ultimate metric for these machines, which is reliability. In a factory setting, a robot needs to work an 8-hour shift.
Right.
The motors can't overheat from continuous use. The grip strength must be perfectly calibrated so it doesn't crush delicate inventory, but doesn't drop heavy metal parts.
It has to be just right.
Yeah, and most importantly, it cannot require human intervention. If a factory owner has to hire an engineering team just to follow the robot around and reset it every time it falls over, the machine is a financial liability, not an asset.
So the goal isn't making a machine walk, it's making a machine walk 10,000 times without a single failure.
Exactly.
But factories are still, for the most part, highly controlled, predictable environments.
True.
To be a true general-purpose platform, these robots have to step out of the warehouse and deal with unstructured chaos.
Which is where the technological leaps showcased at the Beijing exhibition become truly staggering. When you move from lifting rigid boxes to manipulating unpredictable objects, the software requirements change fundamentally.
Yeah, I was reading about a specific white humanoid robot at the event that was standing at a table folding cotton shirts.
Ah, yes.
And my initial thought was, okay, we've had machines that can stamp out car parts for decades. But the reports noted that it wasn't just clapping the fabric together, it was using articulated mechanical fingers to feel the fabric and actively smooth out the wrinkles before making the next fold.
That is a phenomenal engineering feat. Oh, absolutely, because fabric is non-rigid. Traditional robots excel at handling rigid objects, right? Like a steel car door is always the exact same shape.
Right.
But a cotton shirt folds, sags, and wrinkles differently every single time you touch it. For a robot to smooth out a wrinkle, it must possess incredibly advanced tactile feedback.
So it's actually feeling the shirt.
Yes. The microsensors in its mechanical fingertips have to measure the tension of the fabric in real time, pulling it just hard enough to flatten it, but stopping instantly before the tension rips the material.
Wow, it's constantly reading the physical state of the shirt.
Yeah.
And the conference showed robots doing this with things that are moving, too. Like, Unitree Robotics had a humanoid that was dynamically playing table tennis with human visitors.
Right.
And not just returning pre-programmed lobs, but actually playing the game.
Which is incredible. If we break down the mechanics of what is happening inside that robot during a ping pong volley, it is mind-bending.
Okay, lay it on me.
The robot is using machine vision cameras, capturing frames at incredibly high speeds. It has to isolate a small white sphere against a visually noisy background of human spectators and bright lights.
It has to filter out all that visual garbage just to see the ball.
Exactly. Then it calculates a three-dimensional arc based on the ball's current trajectory, factoring in velocity and gravity. It predicts exactly where that ball will be in the next half second.
Half a second.
Yeah, and then it decides on a paddle angle, calculates the necessary physical movement, and sends electrical currents to its arm joints to execute a physical swing. And it performs that entire sequence of data collection, vector math, and physical reaction in a fraction of a second.
It is reacting dynamically to the world instead of following a script.
Right.
And it is not just bipeds doing this. The reports heavily featured quadruped robotic dogs navigating simulated rough terrain with heavy payloads.
Yes, the quadruped models.
Because they have 4 points of contact and a naturally lower center of gravity, they can handle outdoor logistics, industrial inspection, or emergency response in places where a two-legged robot would just sink into the mud or trip over rocks.
They trade the human-centric adaptability of two legs for raw stability and terrain traversal.
Oh.
But what we are seeing across the board is a push to move these autonomous machines out into public civic spaces.
Which brings up Amoga Robotics, backed by the automaker Sherry.
Right.
They actually showcase traffic control robots dressed in high-visibility officer uniforms.
Oh, yeah.
And the fascinating part is that these aren't just concepts. Like, they have already been deployed across dozens of Chinese cities. They stand at intersections, monitor traffic flow, identify violations, and actually physically communicate with drivers.
It represents a radical merger of municipal infrastructure and autonomous robotics.
Yeah.
They are taking the machine vision we just discussed in the table tennis robot and applying it to complex urban traffic patterns, replacing stationary cameras with mobile interactive units.
That interaction element leads right into what UBTech Robotics presented.
Okay.
They brought a humanoid designed specifically for companionship and emotional interaction in the home.
Oh, wow.
Yeah, it features synthetic skin, animated facial expressions, and it's meant to communicate naturally with people. But building a machine that can read a room seems fundamentally different from building a machine that can swing a ping pong paddle.
It is a totally different computational universe.
Really?
Yeah. Building a convincing social robot requires integrating disparate technologies to fire in perfect unison. It is about balancing, yes, but it's also about naturalistic movement, speech recognition, conversational timing, and emotional responsiveness.
Because humans are incredibly sensitive to timing.
Oh, very much so.
Like, if a factory robot pauses for 3 seconds to process data before lifting a crate, it doesn't matter. But if a companion robot is having a conversation with you and it freezes with a blank stare for 3 seconds while its cloud server processes your sentence.
It plummets straight into the uncanny valley.
Yeah, that's creepy.
It feels unsettling and alien. The latency of the software has to match the natural rhythm of human biology. Furthermore, a companion robot operates around the elderly, around children, or in messy living rooms.
Right.
The force-sensing algorithms we talked about with the cotton shirt now have to be applied to human safety. The machine's expansion decision-making hierarchy must prioritize not causing harm above all else, adjusting its physical force dynamically if a child suddenly runs into its path.
Looking at all these different applications, factories, traffic control, companionship, the scope is massive.
It really is.
And the event really underscored that this isn't just a bunch of isolated tech startups tinkering in garages.
Yep.
Humanoid robotics is currently the center of a massive geopolitical technology race.
Yeah, if we zoom out to the macro view, the strategic stakes are immense. At the opening of the event, Vice Minister of Industry and Information Technology, Shin Guoibin, made it very clear that global robotics leadership is a top priority.
A top priority.
Yes, and that makes sense, because mastering humanoid robotics requires a country to master almost every other advanced tech sector simultaneously.
It's like trying to conduct a massive symphony.
Exactly.
The artificial intelligence acts as the conductor, the sensors are the sheet music, the advanced semiconductors are the processing power, the high-density batteries are the energy, and the precision motors are the instruments.
What a great analogy.
And if one single section of that orchestra is a millisecond late, the entire performance collapses.
And that is why the international presence at this conference was so heavy. Buyers from Southeast Asia, the Middle East, and Latin America were scouring the floor for technologies they can apply to their own agricultural sectors, infrastructure inspection, and security.
Yeah, I noticed the security aspect came up frequently in the source materials.
It's a big part of it.
Like, Governments globally are paying very close attention to the implications of deploying autonomous, dynamic machines. We are approaching a reality where independent thinking hardware is navigating public streets and private facilities, which requires entirely new regulatory frameworks that most countries haven't even begun to draft yet. Now, we're not taking any sides here, just reporting what's in the sources, but it's a huge shift.
It is a genuine paradigm shift. But the developers on the floor know the technology still has to prove itself physically before it can conquer the economy. Which is why the exhibition booths weren't even the ultimate test at this event.
Oh, right. The ultimate test was the World Humanoid Robot Games.
Yes.
Which kicked off on August 22nd. They had more than 2,000 robotic competitors entered into athletic and agility challenges. These machines weren't just standing behind a velvet rope folding laundry.
Right, no controlled environments here.
They had to run, navigate complex obstacle courses, and respond to actively changing physical environments.
And if we return to the biomechanics we discussed earlier, running is exponentially harder than walking.
Because of the massive physical forces involved when a machine that heavy leaves the ground and lands again.
Precisely. In walking, you generally keep at least one foot anchored, so your center of gravity is supported.
Okay, that makes sense.
But in running, a robot enters an airborne phase where it loses all contact with the ground. When a 150-pound metal frame lands on a single foot, it generates massive kinetic energy.
Wow, just all coming down on one point.
Exactly. The servos, which are the tiny, high-precision motors driving these mechanical joints, they have to absorb that violent shock instantly without snapping.
And while it's absorbing that shock, the computer has to recalculate its balance midair for the next leap.
In real time, factoring in the uneven terrain of an obstacle course.
That's insane.
It is. The processor is adjusting the tension of the servos, calculating the exact angle of the knee joint to launch the robot forward again, while the gyroscopes try to keep the torso upright. The computational load is staggering.
Which brings us full circle back to that multi-million-dollar robot face planting in a shower of sparks on the exhibition floor.
Yep.
When you lay out the physics of what these machines are actually trying to accomplish, suddenly a crash doesn't seem like an embarrassing failure at all. It seems completely inevitable.
Yeah, and if we connect this to the bigger picture of robotic development, those engineers don't just expect these falls. They actively need them to happen.
Wait, they need them to fall.
Oh, absolutely. Every single crash is a treasure trove of diagnostic data.
I would assume the hardware damage is expensive, but the data is what actually drives the next iteration.
The seconds leading up to a fall are the most valuable part of the development cycle. When the robot hits the mat, the engineering team instantly pores over the telemetry. They look at the sensor readings, the motor commands, and the camera feeds.
Right, to see what went wrong.
They have to identify the exact point of failure. Did the foot sensor miscalculate the friction of the floor? Did the knee servo respond too slowly to the command? Or did the central processor just make the wrong mathematical decision for its center of gravity?
So they literally cannot learn how to stay upright without analyzing the data of how they fall. The source material noted that the technical teams at the conference were working around the clock, constantly repairing damaged components, replacing blown servos, and recalibrating the balance systems just to get the robots ready for the next grueling demo.
Because that iterative data collection is the only path to everyday industrial reliability. They overcome the physical limitations of the hardware one failure at a time.
Looking at everything we've pulled from these reports, the physics of walking, the computational demands of table tennis, the need to gently fold a shirt without ripping it, it really paints a clear picture of where this global race is heading.
It does.
It seems like the ultimate winner of the robotics industry won't necessarily be the machine that looks the most human, or the one that can run the fastest obstacle course, or the one with the most expressive synthetic skin. The company that ultimately wins will be the one that builds a machine that is just boringly reliable.
Boringly reliable.
Yeah, a robot you can turn on, leave alone on a factory floor for 8 hours, and trust that it won't end up sparking on the concrete.
The boringly reliable machine is the one that scales up and fundamentally changes the global economy.
But all of this leaves me with one final thought, something really provocative to chew on based on these readings. The whole premise of these general-purpose robots is that they are being painstakingly trained at massive expense to physically adapt to a world built entirely for humans.
Right.
They are struggling to balance on our stairs, fit through our doorways, and reach our shelves. But if flawless reliability becomes the ultimate economic goal for the massive corporations buying these fleets, at what point does the math flip? Like, at what point do we start quietly redesigning our own human spaces, flattening our floors, removing our stairs, widening our doors, just to make it slightly easier for the robots not to fall?
Okay, one question for you. How do the dramatic humanoid robot crashes at the Beijing World Robot Conference expose the biggest challenges engineers still face in achieving reliable balance, movement, and real world safety? Don't forget to comment it. Thanks.